Okay, so next, elimination reactions. So this is the removal of a molecule, and this is one of the first experiments you did at the start of fifth year, and it's where you're removing something. So back in fifth year, this is the production of ethene gas from ethanol. So when you start with ethanol gas, C2H5OH, you use Al2O3, which is a dehydrating agent. So again, dehydrating agent is going to take H2O out of a molecule. It dehydrates it. And you can see it here in blue. H2O is taken straight out. When that's taken straight out, you can see what you're left with. You're left with 2 carbons and the 4 hydrogens around it. A double bond is formed. So ethene is formed. So elimination is just the removal of a particular molecule. In this case, it's the removal of water. Since water is removed, this particular type of elimination reaction is also referred to as a dehydration reaction as well. So in case you see that, so a dehydration reaction. So that's elimination. Very straightforward, not much to it. Okay, moving on. We're on to redox, or oxidation reduction reactions. So looking at this, we have a primary alcohol being converted to an aldehyde and then being converted to a carboxylic acid if it's in excess. Then we have a secondary alcohol will produce a ketone. And then we can also go from aldehydes or ketones back to an alcohol in reverse. And we can also go from a carboxylic acid back to an alcohol in reverse. And the experiment you need to be looking at here is the reactions of ethanol. So let's start with the first one. Now, it does look like there's an awful lot here, but just take your time and look at it. So first of all, we've got our primary alcohol, which is ethanol. Now, primary alcohol, as we know, is where the carbon that is bonded to the OH group, which is this carbon here, is bonded to only one other carbon. So that means ethanol is a primary alcohol. When you react this with an oxidizing agent, so in this particular example, this particular oxidizing agent is sodium dichromate. So in the presence of a sodium dichromate oxidizing agent, you will end up performing or producing the equivalent aldehyde. So if you have ethanol, you're going to produce ethanal. You can see a double bond OH has been introduced here. If your oxidizing agent is in excess, it will keep pushing past the aldehyde and you will end up with a carboxylic acid formed. Now that's if it's in excess. If your oxidizing agent is limited, then you're not going to get the carboxylic acid, you're going to produce the aldehyde. So that's the difference with excess compounds. The carboxylic acid, of course, produced is ethanoic acid. Again, all 2 carbon. You can reverse that equation, of course. So if you start with this one here, which is the aldehyde. If you start with the aldehyde, you can go backwards. And again, if you're oxidizing in one direction, then you reverse, you're doing reduction. And the reducing agent, or what you're using for reduction in this particular case, is hydrogen gas, and you're using a nickel catalyst. And when you reduce ethanol, you end up producing ethanol. If you move on to the secondary alcohol again, the carbon that is bonded to the OH group is bonded to 2 other carbons. That's what makes it a secondary alcohol. The carbon that's bonded to the OH group is bonded to 2 other carbons. So in this case, we got propan-2-ol. And propan-2-ol, again, when it's oxidized using your Na2Cr2O7 oxidizing agent, produces propanone. It introduces the C double bond O. And again, that can also be reversed. So if you're starting with your ketone, so in this particular example, when you reduce the ketone using hydrogen and nickel catalyst, you end up producing the alcohol. But in this particular case, it's again a secondary alcohol. Moving on, now what we've got is the reactions of alcohols and carboxylic acids as acids. So the first thing you have to look at is the reaction of an alcohol with sodium. So what we've got here is C2H5OH, so that's ethanol. And then when that reacts with sodium, what you're going to find happening is the hydrogen here leaves. Now over on this side, when that hydrogen leaves, what you end up forming is C2H5O Na.
and that's plus H2, which is your hydrogen gas. This compound that's been formed is called sodium ethoxide. Now this is included in this because if you look at what's happening here on the left, at this particular part, ethanol is essentially letting a hydrogen go. It's donating a proton. So in this particular example, ethanol is acting as an acid. When the sodium joins on, your sodium ethoxide is formed and hydrogen gas is formed. This is also a balanced equation. So you would have 2 of those, you would have 2 of those, and you had 2 of those. So that's the first part. Moving on to the next part, why do carboxylic acids act as acids? Well, the two main reasons is the inductive effect and the stability of the carboxylate ion. So let's have a quick look at the inductive effect. You don't need to go into too much detail here, but when you're talking about a carboxylic acid, why is it an acid? So first of all, we've got a C double bond O and an OH. And this particular part is called the carbonyl group. And in a carboxylic acid, the C double bond O part, or the carbonyl group, this has an effect of drawing electrons away from this OH group here. And when it draws electrons away, what happens is the hydrogen tends to leave. So again, if your hydrogen is leaving, you're donating a proton. So if you're donating a proton, then of course you're going to become an acid. Now some students say to me, well, of course a carboxylic acid is an acid, but it's only an acid because of this fact. The second part of it then is the stability of the carboxylate ion. So the carboxylate ion is this, it's C double bond O, and then it's an O with a minus. So when the H actually leaves, it forms this thing here, which is your carboxylate ion. Now, what we have here is we have a stabilization. We have a thing called resonance. So resonance, or you may see it described as delocalization of electrons. There is a very even share of electrons across this particular ion, which makes it very, very stable. And because this is very, very stable, it makes the hydrogen easier to leave. So because the ion is very stable, it's more likely to let the hydrogen go and therefore become an acid.